Okay, so it's almost time to start. I will start slowly so that people that come can have a chance. So just let me go to the start of my presentation. So yeah, it's like probably this page. And hello everybody. Its talk is Lambda HardCore. For Vox Days Ticino. Nice to see you here. So about me, maybe for those that don't know me, I'm Jarek Ratajski. I'm developer, wizard, you sometimes see it, and an architect, written this way. I spent last 17 years with JVM generally, so I'm mostly wizard of JVM, and that's my Pokemons are as follows, yeah, Java, Scala, whatever. Yeah, and working and spend my life in Lucerne working for CSN's Versicherung. So CSS insurance, we don't insure style sheet yet. The company was founded like, you see, over 100 years ago. You know we have some legacy code. Well, it's okay. Okay, so what is the talk going to be about? So the first thing, warning for you. Once I forgot this talk is completely useless. Sorry for that. If you are counting on seeing something like, I don't know, great stuff you can do with Java Lambdas, yes, it's great stuff that you can do with Java Lambdas, but not on your production. Never. No, not in a normal business life. It's something for fun. So we'll be talking what's a number. It's a very important question. What is, well, I will show you something like lambda calculus. Who knows lambda calculus? Oh, a couple of you, so it will be something like recollection or things from university. I will present that in Java. That's the core point of this presentation, and yeah, we'll have some fun. So, maybe why did that come to that point? I must say I'm not a scientist. So sorry for those of you that rely on me, then I will be explaining very deep scientific stuff. Not. I am a real developer just. So. However, I studied mathematics, and so I learned a little bit this stuff, but I studied mathematics only because of this. So by the time I was to choose my studies, I was like mastering this machine, Commodore 64. Who had Commodore 64? Yeah, that was the greatest machine of all times, come on. You know, and I was able to do that. So being able to do that means, yeah, there's nothing you can learn at your studies. Yeah, come on, it's just the top level that you can achieve in computer science. So for me, studying computer science was just no sense at all. And I had a colleague that was able to do this on his PC with Hercules graphic cards. So because of that, it's only black or white. So he had the same problem. There's nothing he could learn more. So he proposed that we'll study something fun. It would be math. So I went to study math, and that was my first lecture. The professor was doing a proof that 1 indeed is different than 0. Oh my God. He spent, I don't know, like 15 minutes proving that 1 is not 0. But you know, the first time in my life I've seen that it indeed is different. I could prove it since that moment. And first time I had doubts about it. But okay, the question is, what is 1, what is 0? That's a very interesting question. So what is a number? In fact, who knows what is a number? Can you explain me? 3? What is 3?
The successor of 2.
Oh, what is successor? Yeah, that's in fact, okay. Successor 1, 2. But what is this? Can we define it better? So, yeah, because, okay, come on. I can have 2 things in my hand, like, but I really like, for instance, if you have a coin. I don't have by the moment coin, but if you look at the coin, like 2 euro, it's great, or 2 Swiss francs. It's funny because one thing and it represents 2. Isn't it crazy? Yeah, so number is something more than just counting items. It's something, some abstraction. And how to define it? So about the number 2, like if we don't have coins, if we don't have apples, shoes, people, we don't have anything to count. What can we use? Because let's suppose this represents Big Bang, the start of the universe. Let's suppose it didn't happen. Our universe wasn't created. And even for those of you that believe there was a flying spaghetti monster that created, no, For a moment, let's pretend there was no flying spaghetti monster. So universe wasn't created at all. Can we represent numbers somehow without apples, without water, bottles, whatever? So mathematicians considered this problem to create mathematics so abstract that it wouldn't depend on the real life, and they come with something like set. You know, who can define a set? Of what kind of things? We don't have things. Nothing was created yet. The universe is empty. You can't have a group of things. So basically, mathematicians don't define set. Set is something abstract. They say, we don't define what set is. Sets exists. But in a universe that wasn't created, can you have at least one set? Yeah, great. So universe wasn't created, but we have one thing, empty set. Isn't it great? Creating things out of nothing. That's cool. So we have an empty set. Okay, great. We've started. We are gods now. We have one thing out of nothing. Can we do further? You in fact, so set is a group of things. Do we have thing right now? We have an empty set. That's a thing. So we can create a set that contains this set. How cool. Great. So we have empty universe, not created, and we already have two things. How great. Yeah? We are very powerful with nothing, just mathematics, just abstraction. So it goes further. I don't have time to explain everything, but there is a procedure. This procedure says, let's take this set before the things that we created, make an union with this thing as an element. So basically, for instance, next thing after this set containing empty set is this set containing an empty set and empty set contained in set. So looks strange, but it's basically 0, 1, 2, and operation known as successor in mathematics. So that's how the classical mathematics was created. The question is, okay, then it's a tree. The question is, why do they do that at all? This stupid play with sets. There was a reason behind, because if we are able to precisely define the structures, the fundaments of this mathematics, so we know which language we talk, we know the rules, maybe this mathematics will be somehow automatically working. Maybe we'll reach something that was like 100 years ago the holy grail of mathematics. That's a picture. Like David Hilbert stated this. If we have good axioms, the basic, the fundaments, maybe we will find an algorithm that using these fundaments will prove automatically every theorem. So like Fermat's theorem, every complicated Pythagoras theorem will be just automatically proven because our language, our fundaments are good, well defined. That's engineering. No more abstract mathematics. That's just engineering. So how cool? Would it be great, yeah? Mathematicians were thinking about how to make themselves useless, like computer scientists doing machine learning. Okay, but yeah, somehow. But there are some, this was known as set theory and it was working well. In fact, it's still working well, in fact, but there are some problems. This was, let's consider the set of all sets that are not members of themselves. So, okay, it sounds complicated. There is this thing. In a city, X like Lugano, there's a barber who shaves all men who don't shave themselves, and only men who don't shave themselves. Okay? And now the question is, does the barber shave himself? And I don't spend much time on it, but there is no good answer to this question. He can't shave himself because he only shaves the men that do not shave themselves. So it's like, and also he must shave himself because otherwise he would be forced. So it's stupid, but that's a paradox known as Russell paradox. And that was a paradox that was killing this fundamental set theory. Like they started with 6, 7 axioms. So these fundaments, what is a set, the set as a just axiom and some other fundaments. And then they came to such paradox. And how to solve paradox? It's the same as you do in a normal life. You start a system with a clean requirements, this, then you design a framework for that, it's great. Then comes the business and changes the requirements. And everything collapses. The same thing happens in mathematics. So came such paradox, and they had to put some crazy hacks to not those paradox happen. So after all, if you set a seed theory right now, you can go to Wikipedia, you will see that it has like 6, 7 axioms that are very, very clean and understandable. You will know what it means. And then 6 others that are just crazy. What is this even? Those are hacks. Nasty hacks on production to make everything working. So, you know, maybe it's just not clean framework. Maybe we should do something better. The new system. Let's start again. So there was a guy, Alonzo Church, in 1930. He started something new. Let's forget about this set theory. Let's start with something else. Let's take a function as this fundamental particle. Set wasn't good enough. Let's take a function. Who thinks it's crazy? Because you know, what's a function? Who knows what the function is? Yeah, so you already see this. In order to have a function, you need a set. Stupid. where is something new? But okay, we'll go over that. So a function sounds stupid, but let's think about for a moment. Let's build world with functions. So once again, new world function. So universe wasn't created. There is not even empty set there. Again, start from scratch. Can we define a function? It's a function that doesn't need anything to exist. Yes, what's identity function? What is this? So yeah, that's the function that doesn't change anything. So it takes whatever. Okay, whatever at the moment doesn't exist, but would take whatever and will give the same thing back. So in order to describe this function, you don't need anything. That's cool abstraction, identity function. So, okay, we've created something. Identity. We have, once again, empty universe, and we already created something. Identity function. So what can this identity function in this moment accept? So itself, because we have one thing, identity function. So it's function that, for instance, can take an identity function and will result with identity function. How cool! We are powerful. So we don't need anything and we can play with that. Okay, cool. So that's how mathematicians, so that's proposal, how to write identity. By the way, it's very simple. You would write it f of x from x is x, sorry. And I'm sometimes using Polish words. But the Alonzo Church notation proposed this. Lambda, I don't know, fancy symbol, from x, dot, after dot you write what it is, it means x. So that's how you write identity with this notation. And yeah, maybe we can, if we go further, basically lambda notation is like this. Lambda from x, x is the variable argument, dot, and after that any expression. What do you do with x? What do you do with that? So that's the formalities you will find on Wikipedia, whatever. So just 2 examples. Lambda from x is x plus x, or lambda x is sinus x. Those are good definitions. But those are bad, in fact. Who knows what's bad with those definitions at this moment? We don't have yet, in an empty universe plus, we don't have sinus, whatever. So we don't have those operations. We have to define them. And we'll do that today. Okay, not all of them, but we will see. So the only thing we will have in this universe, empty, only one thing. Ability to define something like lambda with this expression. And inside of the expression, we can use something like this. Lambda from x is, for instance, f of x, from x. And what is this f? It's just another lambda. What is this space? That's the most important operator in lambda calculus. It's so important that mathematicians are afraid to write it. It's function application. So it's in lambda calculus, function application is just a space. You don't talk about this. It's so important. Okay, but nevertheless, it's very simple. So we will have only 2 things: ability to define the lambdas and ability to apply lambdas. But what do you do? Lambdas are functions, basically. Okay. So let's play with that. Okay, if for you it's not clear, we'll do that in Java right now. That's the goal. So how to define lambda in Java? What is this in Java? Okay, it's easy. I will start with that. It's functional interface. How cool. And it's public interface. I would call it Lambda. Okay? So the question, what to write here inside? Apply. Apply from what to what? Wrong. What is the domain? Exactly. So we'll write something that results with lambda, takes another lambda. That's it. That's the lambda in Java world. How cool. So we can maybe play with that. It will be very stupid, but let me define this. Like lambda identity is like this. Easy. What can we do with such identity? Oh, I will do something very stupid. I will display it. Sorry, it's Maven, it's slow. So you see, it's like this. So I've just printed some hash of an object. Doesn't make any sense. But we'll see that something is in fact working. If I apply identity to itself, like this, you will see that this thing works, because after doing identity with identity, I get the same number. So you see it's working. So this is how I will define whole mathematics today. Java with anything, but one exception. I will only define lambdas. Inside of those lambdas, I will use other lambdas and applications. I will not use Boolean. I will not use integers, whatever. I will just do plain definitions of lambdas, so purely functional, even more than purely. One exception, in order to print it in a sensible way, I will use some other package. This package, what it takes this identity definition and tries to print what it is in a mathematical way. You will see that, okay? Because otherwise, playing with such crazy number doesn't make much sense. So but before I go further, I will just go back to the mathematics for a moment, just to show it a little more data. So we know how to play with identity. Can we create yet another function? Identity was easy, without using anything from external world, like plus or sinus. So there is a possibility, like take a look at this. It's a lambda from x that results, by the way, it's associative, so it results with lambda from y returning y. So it's basically, you can explain it's lambda from x that whatever x is, it just ignores it and returns identity. It's other lambda. It's not identity, it's other lambda, because also you will see that basically it's a function of two arguments. So lambdas are basically functions of one argument, but that's not a problem, even though you can have two arguments. This is how it's done. Let's play with that. So I will show you. If we have this function, lambda from x returns lambda from y that returns y, and we apply it. By the way, I'm not afraid to write this, so I'm using underscore. I write the function application. We apply it to the two objects that I borrowed from a different world, like trumpet and tomato. Okay, just for a moment. Let's borrow those. So after the first application, in place of x, I will use trumpet. But you see, because x was not used in an expression, in fact, it returns lambda from y, returning y, and then tomato as a second application. Then I apply it tomato, of course, because it's identity, it returns tomato. So you see, we have something. That's how lambda calculus works. So there is also another possibility. I create that function, lambda from x, that returns another lambda that takes y and still return x. That's something else, because if we do the same operations with a trumpet and tomato, we get, after the first x, if we apply this trumpet, then we get lambda from y returns trumpet. And then it's still applied to tomato, but because it doesn't use tomato in expression, it returns trumpet. So those are two different functions that we created basically with nothing. And there is a possibility to use something like that. Lambda from x returns lambda from y that returns x applied with y. But the problem is I can't write it, because if I apply trumpet and to tomato, I will break trumpet. Yeah, so sorry, I don't do that on stage. But OK, let's do that in Java. It will be easier. So first of all, I will show you how this package for displaying works. So this smart display is the only thing that I will be using from the external, so only dirty thing. It displays simply, that's identity, so mathematical definition. Then I will play with that. Well, you see this function funny? We've just defined it before. So I'll display it. It's like this, okay? It's working. The system is working. I just defined some funny lambda. Right now, let me do this. I define lambda that's called true. Basically, it's the same lambda as this funny, but for a reason, it's called a true. By the way, it doesn't matter how it's called. It only makes matter what's inside. But we'll see that. So I will display this true, but even before going further, I'll do something more. I will define lambda called false. As you see, those are exactly those two lambdas that I was discussing before, but this time with Java. So you have something that we call true and false. Yeah, okay, that's just the names, but not coincidence how they are called. So if I create another lambda called end, like this, I can even display it. By the way, I will show you something. If I display it, I will have this true, false, and end. And by the way, if you are concerned why this is here P and Q, that's a conversion that mathematicians use. And by the way, my package for displaying, it basically doesn't know which names are there. If I delete this P here, I will get the same with X and Y. So it's just a matter of convention. I am displaying using this convention with P and Q. So to make it consistent with things you can read, for instance, in Wikipedia. So if after this talk, you can go to Wikipedia and recheck all of this. It's a standard thing, but you can recheck that with Java, exactly with this step. So we have something that's called AND, true and false. Let's play with that. I will create something called result1, apply if it with false and true. As you see, AND is a lambda from two things. So first I apply it once with false, and then I apply this with true. So what will I get? What will be the result of that? For some of you, that shouldn't be a surprise. If you look at the result, it is what? It is the same as a false, you see? So we have operation AND that takes a false and a true and returns something that looks like a false. How cool. So maybe if I write here a true, what I get? Something that is in fact true. And by the way, I said it doesn't matter how the lambda is called, so I can here, for instance, use funny. Funny is again something that is true, because it has the same definition as true, so it should return true. Let's see that. Yeah, it returns true. So it's working AND operation with just nothing. We didn't have to use no booleans, no real booleans, no integers, just pure functions definitions. How cool. So we'll go further. We can create OR the same way, like this. And then I make it on top, like here. Result from OR. So I will use it with a false and a true. So let me show you that. So right now we have OR with a false and a true, and it returns true. I will spare my time proving you that it really works with all the possible values. Or is it unclear for you? Mario? Clear or not? Okay, great. So if it's clear, it's just working. You can prove it with a pen, or you can prove it with Java. So how cool. Even you can go further. That's a not definition. It's a little bit longer. And then, for instance, I will display not from false. So this is this. Okay. And so not from false is again true. So what I've defined here is the definitions of true, of false, and 3 Boolean operators. This means we have Boolean algebra covered with just nothing, just pure lambdas. How cool. It works. But okay, you may say, okay, Boolean algebra is something easy. 2 things and just the end, yeah? That's not really great thing. So let's do something more interesting, like this, 0. Do you recognize this 0? So you should recognize it. Or you have seen already that. No, it's not identity. It's something that takes something and returns identity. So it's already known under the different name. No, it was false. And it's ultimate proof that the creators of C language were right. Because they, you know, in C, 0 is false. It's exactly like Alonzo Church took for his lambda calculus like almost 100 years ago. So he already knew that. Okay, so, but we can define 1 this way. So by the way, it's only a convention for Boolean algebra, and for this, that's a convention how you can represent those numbers or those values. There are different conventions. This is working, this is the most popular. There are other alternatives that just operators and everything must fit. But this one is, as I say, the standard mainstream one. So we can define 1 this way and 2 this way. I will just display it and you will see the pattern. Okay, you see that 0 is this, 1 is this, and 2 is this. Basically, it's a function. So what is a number in lambda calculus is a function from 2 things that basically returns something that how many times this f argument is applied with f from x. So it's like if it's once time, it represents 1. So basically, it means you can create successor. So this operator this way. Take some n, take some f, and take some x, and returns, if n is this kind of number written this way, then it will return just one more application of f. So I can represent successor operation. I will only just display it, how it looks, and then I will display you how, for instance, looks successor from 1. Okay. So successor from 1. What is this? As you see, successor from 1 is exactly looking like 2. So it's working already. And we can go even more farther, like right now I'll do something strange. Successor, because you will ask probably, if you are listening carefully, what is this cardinals from integer 10? Because in this moment I'm using integer. I told you I will not use. But if I write there f, apply, it would be very boring for me. So I made a shortcut and I defined this small utility function that returns this. But basically in this place I could write this f from x returning f applied to f applied to f. That would be boring, so that's a shortcut. You don't need it, but it's to make it more readable. It's still working. So behind it's just ordinary lambda. So if I defined plus this way, like you see it's a more complicated operation than, for instance, and or where. Then I can display this plus, just as, so we can display any lambda, so I will display plus. And right now, let's see if it's working. I defined those 2 lambdas. Again, to spare myself time typing those all applies, this is A with 6 times f applied. This is B where is 7 times applied. This. So I will display them for you to show it. Oh, blah, blah, blah. Yeah, almost, yes. So plus A and B. Let me check it. So you see, A is in fact this one. This is written in Java, in fact. B is written with Java this way, has 1 more F, so that represents 6 and 7. And then plus, and you should count all those F. For me, it's just impossible. I can't count only to 3. So I had another thing. Everybody that studies mathematics has this problem. I've created a function that counts how many times f appeared. So this is cardinals to integer, only to display. So again, it's only for debug purpose. So you see, it was 13, so as expected. It's working. How cool. You can, again, prove it on pen with a pen, or you can prove it with Java in debug. It really, you can try it with debugging. But that's up to you as a homework. It really works and doesn't need anything, really. Java with nothing. So multiplication is easy. Looks like this. The multiplication operation, by the way, is the one that you can easily understand why it works if you, why it's looking like that. It's the easiest of the typical calculations. Okay, moment, just make it in front. So if I multiply again this A and B, I should get some kind of a number. Okay, sorry, too much of this. Just, yeah. So I just need to see. So I multiply A and B, and you see, oh, I have 42 because I've converted it to integer, but I don't have to. I could smart display. For instance, this maybe I will check it because I like the. Oops. You know what? I will skip to next slide because I just don't want to play with this code again. But basically it works, and let me skip to something more complicated. Okay? I always lost if I type too many F's. So, okay, working natural numbers, working Boolean algebra. Can we do more? Because, come on, that's fast forward. That's always in front. So that was the problem that, in fact, Alonso Church had. One day he said, okay, plus can be defined, but can we have minus? Okay, we have successor, can we have predecessor, decrementation? It was not that easy. In fact, his student found the student, I know, coworker, so clean, found the way how to represent minus. So let's take this 9 number. So I call it a 9. And let's take a look at this operation. Oh, how complicated it is. You see? It's like, oh my God, oh my God, oh my God. Oh, yeah, it's done. So this is, then I will display even this operation. And then let me show if it really works. I display a 9, and then I'll display decremented in 9. We'll see if it works. You see? Decremented has 1 F less. It really works. How cool. So we can even decrement. It's great. Really, that was one of the biggest inventions in this lambda calculus, how to decrement. And if we can decrement, subtraction is then easier, because basically it looks like this, using predecessor. So we can subtract. I won't play with subtraction, really, because I want to show you something interesting. Because, okay, those are operators on natural numbers, operators. But right now, take a look at this lambda. I call it, not by accident, if lambda. If. It takes some C, it means condition. Takes some T, means in case of true. Takes some F, means in case of F. In case of false, basically. And definition is pretty straightforward. What is this? It's something that we know from every language. It's a if expression. By the way, it's an expression, not statement. So if the C is our false or true, as defined previously with this convention, then providing some other lambda as T or as F, we will get either T or F evaluated, depending on the conditions. So we can represent the, I would say, basic brick of algorithm. If expression. How cool. And we can go further with that. For instance, this is 0 is a condition. By the way, again, something to not repeat every time this lambda from x returns y, returns lambda from y, that returns y. This is basically this thing, and this is the opposite, the true definition. I have them under, that is this Jarek Boolean, in fact here, in a Bedlam package. It's basically this standard definition of true and false as a lambda, really. So it's nothing magic here. So, for instance, this is the less or equal condition. I'm printing it here because I will need them. So just a moment. Let's go to here. And now we have these conditions. We have if. We can build something very crazy, but we need one more thing. So this is something that I really like, and it's called autocall operation. So it's lambda that takes one x and returns x applied to itself. You know, it's a very rude lambda, very impolite. It might go on and do it to yourself. Okay, it's a very bad one, but I love it. And then using this lambda, you can create something like this. Who knows this stuff? Because this is very, very famous thing. Y. This is something known as Y combinator or fixed point combinator. Well, there are a couple of different names because it's one of the biggest breakthroughs made in lambda calculus. Why do we need it? I will show you. I will show you by writing some other function, some other lambda. Lambda from called G that takes some R, but forget about R for the moment. Look at this N. If so, it basically takes some N, and if N was 0, then I return 1. Otherwise, I multiply N, forget about this R for a moment, with predecessor of N. You know this thing, maybe. Moment, just let me see if it compiles. You know what this is. So take some N. If N is 0, then I return 1. Otherwise, N multiply with predecessor from N. Not from predecessor from N. Predecessor from N with this function. It's a recursive definition. What is this? Okay. Factorial, exactly, it's factorial. So almost, so I write lambda factorial, factorial is y applied with g. So I will in a moment explain you why I needed those tricks. Or some of you may find it. Okay, sorry, I make it up. So I will play with factorial from 3 for a moment. Like, let's print it. Factorial from 3. Just let's print it. You see, factorial from 3 is in fact 6. That you can count, or 6 times f. So if I print here 6, then I will get something crazy. Wow. You could count all those f, or you could believe me that it's okay. But maybe, okay, if you don't believe me, I already have this function that counts how many f's I have here. So this is the thing. And basically, the question for you, who knows why this strange fixed point combinator is needed? Why it's not really normal recursion there? Because if you define factorial normal with every language, you can use this function factorial from n minus 1, and it's okay, yeah? Why it's not working here? There is a simple reason for that. Because if you define function, like here was factorial, you can inside of the body reuse this symbol, factorial. But if it's the variable definition, g, for instance, you cannot use this g here inside. So because of that, this simple trick is needed. So because of that, this trick is needed in lambda calculus, that you go with something intermediate that basically is I would call it, that's not a factorial, that is a factory of factorial. And this y combinator changes this factory of factorial into the real factorial. Basically, you can do the same with Fibonacci, whatever recursive function. So this magic operator, magic lambda, that takes something and returns recursive version of this. How cool. It's really magic. So, okay. So what I've shown you today is that really this Java with nothing or lambda calculus, pure functional language is powerful, can do all your mathematics from scratch. Again, you can define everything, and basically it's true. If you don't believe me, you can believe Turing, because he's proven that lambda calculus and Turing machine are equivalent. They are enough power, both exactly so powerful. So anything that you can do with a Turing machine, you can do with lambda calculus and vice versa. Okay, isn't it great? So we have powerful tool. So maybe right now let's go back to our holy grail. So we have very, very, I would say, elegant formalism, lambda calculus, that is very powerful. So maybe we'll do this trick. What is a theorem, like last Fermat theorem and Pythagoras? It's basically a statement. And lambda calculus, in fact, it's more complicated, but it is like this. You can represent statements, logical statements, with lambdas. You see the point. Then I simply evaluate this statement and find out if it's true or false. Oh, magic! So I can simply take any complicated theorem that mathematicians took, I don't know, 50 years to prove, and just simply evaluate if it's true or false. Isn't it great? So all the problem is gone. So we can read how to do that, but basically it's not really working. Why it's not working, you see on this picture, on this not nice autocall lambda. If you do autocall with autocall, so once again, nasty operation, you will see this. Let's wait for a moment. Stack overflow error. So unfortunately, in any real complicated, realistic statement with lambda, happen such lambdas that you can describe mathematically, you can reason about it, but unfortunately, in any automatic calculation, they explode with stack overflow. Basically, it means it's the same problem that you know from Turing machine. You can't tell if it stops. You can't use another Turing machine to just say, does it stop or not? So basically, Jarek has proven that no computable function can decide equivalence. It means you can't build lambda that takes another lambda and just say it's true or false. Oh, such a story. So, but you don't have to worry. If you go to Stack Overflow, you can in fact find the solution. I wasn't brave enough to check it, but people are working on that. It's a really long story behind that. With C#, they are building the equivalence. So basically checking if two lambdas are equivalent. So basically, if you do that, if you have an operation that checks two lambda and say they're all logically if they are equivalent, then basically you've broken this halting problem or whatever. I think they haven't studied anything, but maybe that's a chance for them. Maybe they will find something. I just count on them. Okay, so right now maybe it's to something more abstract. Okay, so we had this set theory that was not elegant. It's working, but it's not elegant. Then we had this lambda calculus that's very, very elegant formalism, but at the end you see that has the same problem, in fact, as any other formalism. You can't have this holy grail. So maybe we should choose something else. Who thinks there is something else that can help us? So basically, there are a couple of other formalisms, like lambda calculus, the recursive functions, or whatever. There are different names. You can read about them. But basically, unfortunately, it's proven that whatever formalism you take, if it's complicated enough, so it's good enough, so very minimalistic you can take and it will be okay. But if it's complicated enough to do arithmetics, so plus, minus, whatever, then unfortunately, there is a proof that this formalism wouldn't be able to prove itself simply like that. It's proven. So basically, Kurt Gödel made this proof even at the beginnings of the church works. So, and church knew this thing already. Basically, funny thing about this definition that if you go to this theorem, you see that simply he creates such statement that is true, but you cannot prove that it's true. How cool! It's really funny. But okay, it's a very interesting procedure. So summary from today for you. Funny thing, I told you it's not really usable. Yeah, but you can do it in Java if you want to learn about it. So if you want to learn about lambda calculus, you want to impress your friends, the girls, whatever. And then you can do it in Java, and you can really, because if you go to Wikipedia and read about lambda calculus, it's all with these mathematical terms. It's not really readable. If you do it with Java, for me it was way easier. Or with Scala, it works basically with any language. I've skipped a lot of problems. So in lambda calculus, we have a problem called eager-lazy evaluation. Those are complicated, but you can, once you start, you will see where's the point. But that's funny thing shows that basically, if I was able to do that with just pure function definitions, oh, come on, then everything can be done with purely functional. That's no excuse for you, for your colleagues. Tell them. If somebody says, no, it can't be done functionally, oh, come on. Then show this video to them. Okay. That's one point of the story. If you want to read more about the topic, after this, if you go to Wikipedia and read about lambda calculus, it's really well done. And you will read it way easier. There is a great blog which presents C# version of this talk. So we are doing this thing mostly at the same time. So I was even using the blog while it was written to make some things easier to understand. But it's really deep. So it really goes into the details to a lot of things I couldn't present. But there are really a lot of articles. So you can spend a month reading that. Dixon blog C# version of that. I like the book, which isn't really about lambda calculus. It's about mathematics, Turing machine. But it's really inspirational, so I recommend it. Emperor's New Mind, Roger Penrose. And this book briefly describes the lambda calculus, but I really say if you read the first part of the book, you will be eager to learn more on all these topics. So I like, because of that, I propose it. But if you, there is another paper, I think it's not that old, in fact, Philip Waller propositionized types, that somehow connects these things, these abstract things, with a modern, I would say, researches that we do in a functional programming, propositionized types. I also recommend it because it's very, I would say, funny article, funny paper. You will be laughing while reading it, and still it's very deep. So it's like, and it doesn't really have a lot of math. Okay, it has a little bit, but it's really, really interesting. So after reading this, you will find like 50 other articles to read. So it's great, more knowledge. If you want to play with those lambdas, you can use on the GitHub, this package called Bedlam. It's basically lambda visualization. I use it today to transfer Java written lambdas into mathematical written lambdas. So it's like this only. And this presentation can be found on this tiny URL. And basically that concludes the talk. So thank you very much. Don't forget to vote. Do you have questions? Has anyone question? Okay, I knew this. It's useless, but. Okay, great. Thanks. Okay, so bye.